Okay, so we started reviewing vectors the other day. There's different kinds of notation, and we had a brief discussion, so let's review that and get to a blank page. Our screenshots. Those guys there. All right, so I like playing with GeoGebra because it does vectors pretty well. And so here I've got two vectors. I've got the vector u, which we'll put a little hat over it to indicate a vector. And then we use angle brackets. So u is the vector 1, 2. And then I have the other vector v, and v is the vector 3, 1. So some things that are important in playing around with vectors. So let's review a little. This is the rectangular version of the vectors. But vectors can also be given in polar form. And so often with vectors, we might take vector v and want to rewrite it in terms of a polar. And usually when I do polar, I do r semicolon theta. We'll still put it in angle brackets, but we can state it either way. So just a reminder about calculating that. Anytime we play with vectors, we consider a right triangle with x and y components, and then that's going to lead to a value for r, the distance that we move, or sometimes called the magnitude of the vector, and then we have theta right there. And so we know some relationships for the polar version. We know that r is equal to the square root of x squared plus y squared. Often we call r the magnitude of the vector. We know that the tangent of theta is y over x, or reversing that, we'll use theta is equal to the arctan of y over x. Does anybody remember the range of angles the arctan has to work with? The arctan ends up only with angles between pi over 2 and negative pi over 2. So the arctan can only place us in the first or fourth quadrant. So if our vector's in another quadrant, then we have to adjust using pi to get there, or sometimes 2 pi. Some other things we know, let's see, what else do we have? We know that y is equal to r times the sine of theta, and we know that x is equal to r times the cosine of theta. So we have ways to travel back and forth between polar and rectangular versions of a vector. And it depends on the situation. Sometimes rectangular is better, sometimes polar is better. Mostly we'll be working with rectangular coordinates with vectors, but every once in a while polar might pop up and we might need it. A reminder, we're used to talking about degrees with angles, but anytime we do calculus, we need to work with radians. And so we might have some conversions back and forth between radians and degrees, so that's important to think about. Some other things about vectors. Get a new page here. Let's try this one maybe. Okay. So considering those vectors I just had, let's draw y-axis right there, x-axis right here, and let's scale it by every other one. So we were just looking at that vector v, which was that guy right there. And the vector u, let's make u red, that was what, 1, 2? So if I were going to do some arithmetic with u and v, there's a variety of different kinds of arithmetic we can do with vectors. So vector arithmetic. There's scalar multiplication. So scalar means to scale. So for example, if we take 2 times vector v, that's going to give us 2 times the vector 3, 1. And that's just a distribution of that 2 through there, so I'm going to end up with the vector 6, 2. And if I look at the vector 6, 2, let's see here, 3, 4, 5, 6 is over here. We know 2 is there. I'm going to end up at that point. If I draw that vector in, it's going to have exactly the same slope or angle as my original vector. So this vector here is 2v. So it just scales it up. So the vector is now twice as long as it used to be, and that's what we mean by scaling a vector. We can change the vector's direction too by multiplying by a negative number, and that just points it through the origin. So that's scalar multiplication. Other things we can do with vectors is we can add them. And this is kind of cool. I always thought addition and subtraction were awesome. So the addition of 2 vectors u and v is just to add their components. So that addition would end up being u has a 1 for x and v has a 3. U has a 2 for y and v has a 1. So we just component-wise add their values, and so that's going to give me the vector 4, 3. I get that right? No, I think so. And let's find that vector on the screen here. Choose black for that one. So 4 is right here, 3 is right there. That's going to put me right here. So draw that one in. So that right here is the vector u plus v. And if we think about geometrically how we got there, thinking about the x-coordinate for u or v, let's say, to do the vector v, starting someplace, say at the origin, we had to move over 3 and up 1 to get there, and then we at this point. And then we're adding on to that the components of u, which was to move right 1 and then up 2. Okay. So what we did, in a sense, is we just took the vector u here and we put it right on the end of v, making this nice triangle. Okay. So anytime you do vector addition, you end up with these triangles, which are kind of cute. Vector subtraction, pretty similar geometrically. That's just component-wise subtraction. So u minus v is just going to be the vector 1 minus 3, comma 2 minus 1, which is what, the vector negative 2, 1. And so if I graph that sucker, let's graph, I guess we'll graph it black. Oh, it's off my screen, kind of. So let's see, negative 1 would be right here, negative 2 would be about over there, and then need to go up 1. So it's somewhere over here. So that vector does that right there. So that would be the vector u minus v. Cool thing about the vector u minus v, if we stick it in this picture, and we can think about it in a similar way. In algebra, how do we think about subtraction? It's adding the opposite, right? And what does it mean to be the opposite in math? How do we define opposite? Opposite direction, so that's kind of the intuitive sense of it, but it has a more technical definition. It's just to multiply by negative 1. So if I think about that idea for a minute, and I say, all right, I had u minus v, that's really u plus the opposite of the vector v. And opposite literally means multiply by negative 1, which means change the direction, right, physically. So that's negative 1 times the vector v. And so we're taking the vector v and we're just reversing its coordinates, or taking the opposite of each coordinate. So if we look at the picture here, starting off with the vector u, we go up, let's see, right 1, and then what's that color? Control Z, choose the highlighter. Green, maybe. We go over 1, up 3 to get to u, and then we have to take these coordinates and reverse them. So that means I want to drop, let's see, I want to go, where did he go? I want to go left 3, 1, 2, 3, puts me over here, and then I want to drop down 1. So it puts me at that vector right there. So we can trace these guys out. But the cooler thing about it is if we grab vector u minus v there, copy it, up, it completes a slightly different triangle based on the vectors u and v. So we have some cool geometry. So let me redraw that in a neater picture. So given two vectors u and v, then if we make a copy of u and stick it over here, let's see. So that's just another version of u, then this vector right here is always going to be u plus v, geometrically, which is pretty cool. And then doing that again for subtraction, that's vector v, this is vector u, then this vector over here is always going to be the vector u minus v. What would happen if I switch the subtraction on u and v geometrically? Thoughts?
It could just be going the other way.
Yeah, it would just make it go the other way. Because if you think about taking the opposite of u minus v, that's going to give me a negative u plus v, which is going to basically give me v minus u. And taking the opposite of a vector just changes its direction. Okay. So if that's u minus v, then v minus u would have to be this vector right here pointing that way. All right. So hopefully all of this is just review. You've seen all this stuff before? Okay. All right, let's see. What else do we need to take a look at? I think those are all the basic things with two-dimensional vectors. Did I miss anything? I've got a wicked fun problem for you guys to do in just a sec. Let's see, vectors in the plane. So we have our notation. Oh, some force problems would be fun to do.
Why do you need a microphone?
It was not working, so I got a different microphone over here that seems to be picking up sound, but I'm afraid to go over to the board because I don't know if it's going to pick me up at the board. So the headset speaker was working, but the mic stopped working for some reason. I got it. Were you guys in here when I had that fancy microphone the other day?
Mm-hmm.
Yeah, I want to get one of those. That seemed like a pretty nice microphone. It seemed to pick things up all over. Let's see. Oh, unit vectors. We need to play with unit vectors a little more. Do that yet. Okay. Unit vectors. All right. So one more boring problem, and then we'll do something more exciting. Page. So unit vectors. They're just vectors of length 1. So, for example, we have a vector we call I, not the imaginary number, but the unit vector in the x direction, which would be 1, 0. And then we have the vector called j, which is the vector in the y direction, and so that would be 0, 1. So x direction unit vector. We talk about magnitude of vectors. This one will be the y direction unit vector. Magnitude of a vector we usually put double bars around it, kind of looks like absolute value, which is just the square root of the components of the vector. So remember, the magnitude is just the length of the vector. And the vectors I and j make up what's called a basis for other vectors. So they're often called basis vectors. Meaning I can build any vector based on these two vectors using scalar multiplication and addition. So earlier we had that vector v, which was, let's see, v was 3, 1. So that could be built by taking 3 times the vector I plus the vector j. And so oftentimes you'll see, instead of vectors being in this kind of rectangular bracket notation, you'll see them written in terms of the basis vectors I and j. Now I and j are the standard basic basis vectors. Any two vectors that aren't running in the same direction can be basis vectors. They don't have to be perpendicular. They can have any angle between them as long as that angle isn't like 180, 0, or 360. You can build any other vectors given any two vectors, which is kind of neat. And there's a homework problem you get to try like that, and we'll try one in a minute. The vector u that we looked at earlier, just forget the little hats, that was the vector 2, 1, no, that was the vector 1, 2, excuse me, 2. That would be just vector I, the x unit, plus twice the j unit vector. So it turns out we can use u and v to build other vectors. So let's just try that for fun. So I and j are pretty straightforward. It's just scalar multiplication, add I and j together. We can build any vector pretty easy. So sometimes you'll see this notation for vectors, sometimes you'll see that one right there. So building other vectors. So let's go again with those vectors I and j, u and v. So 1, 2, 3, 2, 3. Actually, we need a few more numbers. 5. That's y. X, and I have U right there, and I have V right there, and I want to try and use them to build the vector, let's say 5, 5. Let's make it more fun. Let's make it 6, 5. So when we normally just add u and v together, they make a specific vector, right? So that's going to give us the vector 4, 3, which isn't quite the vector I want. But can't I change the length of u and or v independently? Yeah, so what we want to do is we want to find multiples of u and v so that each one extends out just enough so that when we add one to the other, we end up at that point over there. Okay? So we're basically, some people call that using u and v as basis vectors to build a new one. So what I want to do is I want to solve the system, some scalar a times vector u plus some other scalar b times vector v. And I want that to equal my new vector, 6, 5. And so we know how scalar multiplication works. We know how addition works component by component. So if we just rewrite that, what this is going to give us here is we know that u is the vector 1, 2. So if we multiply that a in there, we'll have a comma 2a is what a times u is, plus we've got b times the vector v, so that's going to give me, oops, kind of brackets, 3b, oops, so, comma b, and that has to equal 6, 5. And the key here is that if I add up, oops, highlighter, if I add up the x coordinates, they have to add up to 6. So I'm going to end up with a system of equations up here. So if I take a plus 3b, that has to give me a 6. And similarly, if I take the y coordinates of these vectors, they have to add up to 5. So then I get 2a plus b has to equal 5. And so all we have to do is solve that system any way we can. So let's see, any suggestions for solving this? Substitution, elimination, matrices? What do you like? Yeah, substitution looks good here because I can solve for a or b easily. So I think I'm going to take the top one and solve it for a. And so that's going to give me a equals 6 minus 3b. And then we can plop that sucker in for the a right there. So that's going to give me the new equation, 2 times 6 minus 3b plus b is 5. Let's clean that sucker up. Bless you. So subtracting the 12 over, we get negative 5b is negative 7. Is that right? On a good day. So b appears to be 7/5. Or if you like decimals, would that be 0.6? No, 1.4. All right, so then plugging back in up here, we're going to find that a gets to be 6 minus 3 times that. So what's that? 21/5. 30 minus 21 is 9. So I'm thinking a looks like it's going to be 9/5. So if we scale vector if we scale vector u by 9/5 and b by 7/5, that'll extend them just the right amount so that they'll reach out together and make that vector right there. So just double check. We think the solution here is going to be, let's see, a is 9/5, right? And b is 7/5. So I'm going to have 9/5, comma, I guess we could use decimals. 9/5 would be what, 1.4? So I'm going to have 1.4, comma, 2.8. And then the new scaled vector v, so what was that one? That was 1.2 times 3 is going to be 3.6, comma 1.2. 1.4 and 3.6 add up to 6 on a good day. 2.8 and 1.2, they add up to 5 on a good day. So all we did is extend these guys. So let's see. U that extended 1.4, 2.8, maybe about right here. So that's our new U. And then V, 3.6, just a little bit farther, and then 1.2 that extended out to around here, maybe right there. And when we take that new V and we stick it on the end here, that should reach out to that point right there. So my scale's a little bit off, but I'm in the ballpark. Okay, And the cool thing is, there's nothing special about vector u and v, and there was nothing special about this vector right here. So my point before was, although it's pretty standard to use these two vectors as the basis, we could pick a different set of basis vectors. And you may ask, why the hell would you do that? Well, think back to when we did polar stuff. Weren't some equations, some graphs, some problems easier in polar than they were in rectangular? So it turns out this gives us the power. If a problem seems hard in one coordinate system, like with x and y, we can build a new coordinate system and we can work off that coordinate system. Okay, so just like you can place your center or your origin anywhere you want, it turns out you can build any pair of axes you want. And from there you can do math with it. Because vectors are just little objects you can manipulate, which is kind of neat. What's that?
So I think you did your math.
I did some math wrong?
It's 5, the point is 5, 4, so 6, 5.
Oh, something doesn't add up here? Okay, so
9/5, so it would be 1.8.
9, oh shit, 9/5 is 1.8, and 7/5 is 1.4, and I called it 1.2. Okay, good. Yeah, that didn't seem like it was long enough there. I thought it was just bad drawing on my part. Okay, so this guy should be the 1.8, right? Thank you. 1.8, which makes this guy here 3.6. All right, so let's try that again. And then the other one was supposed to be 1.4. And then if we take 3 times 1.4, what does that give us? That gives us 4.2, is that right? So this guy right here should be 4.2 comma 1.4. All right, let's see if that looks better in the picture. So we extend u 1.8 about there and 3.6 around there. And that looks like it's still in line. Oh yeah, that looks like it's going to reach out much better. V gets to reach out to 4.2 and 1.4. So that's going to be somewhere over here-ish. Pick up that length and stick it here. Yeah, that looks more like it. Yeah, thank you for correcting my bad arithmetic. All right, cool. All right, so now I got a cool problem for you guys. Just a note on, so we don't have enough time to finish all of chapter 11 because we only have one more week after today. So we'll just see how far we get up through next Wednesday, and we'll stop doing new stuff on Wednesday. So I think we'll probably get up to the dot product. I don't think we'll get to the cross product, but maybe it'd be kind of cool if we could do lines and planes in 3D, but I don't think we're going to get there either. And then some other cool things about 3D, I'll just point out. One way of looking at 3D, and then I'll show you the cool problem in a second, is to have a y-axis. That's usually y. This one's usually x, and that one's usually z, right there. And then based on that, you can plot a point. Like, let's suppose I go over x, 1, 2, 3 units, and then I go out y, 1. Let's see, I counted by 1 there. 1, 2, 3, 4 units, and then I'm going to go up z. And that one's going to be harder to count. 2, 3, 4, 5. So we'll go with that one. That's going to put me around right here. So I'm going over this way, 3. I'm going to go over that way, 4. And then I'm going to go up this way. And I was trying to go 5 in the z direction. So that puts me at this point out in space there. Okay? So that's one way to map coordinates. But think about driving around on the planet Earth. Is that how we do things on planet Earth? No, we don't do that. How do we get coordinates on planet Earth? Latitude, longitude, and there's one more coordinate. Elevation, right? That's another important factor, elevation. I mean, mostly we're standing on the ground, but we have an elevation relative to sea level, okay? And sea level we consider like this average distance from the center of the Earth. So another way to think about that point right there is you could instead say, think about this vector in the xy plane right there. You could consider sweeping out an angle that way. And then from the z-axis, imagine another vector connecting from the origin to that point there. Sweep out another angle from the z-axis over to that final vector. So that's like latitude and longitude. And then you have the distance from the center of the Earth to get there. And that's called spherical coordinates. So sometimes we do things in rectangular coordinates. So I'm just giving you a preview of what you're going to see in vector calc when you get there someday in your future. Rectangular, that isn't right. Rectangular, but it is. Okay. So rectangular coordinates is where we write points or vectors in terms of x, y, and z, perpendicular directions to each other based on 3 axes. But there are other ways to write coordinates. So spherical is another one if we think about latitude and longitude. Spherical. Spherical. And spherical coordinates are given in terms of angles. So I think this angle down here is usually called phi. Oops, I should have drawn you in red. This angle up here, I believe, is usually called theta. And then we have r, the distance out from the origin. So sometimes you'll see r, phi, theta coordinates to get to the same point. Okay? And there's a third variation called cylindrical coordinates that are done also instead of spherical coordinates, which I might mention next week in a little more detail. But just to note, just like we have rectangular and polar in 2D, in 3D, there's actually a lot of different options. The most popular are rectangular, spherical, and then another idea called cylindrical, which uses 2 perpendicular coordinates and then an angle. So we can look at that later. All right, cool problem. Hopefully you haven't already done this one. Homework. Has anyone finished the homework? You already finished it? Oh, you did the cool problem already. So this one just blew me away when I saw it in the problem sets. I thought it was the coolest problem ever. It's the last problem, homework set. And I just had a blast doing it. I had to do it 3 or 4 times just for fun the other day. So what we have is this robot right here in the maze. And the robot has to move in straight line paths. Do you have a question?
Okay.
Okay. In straight line paths in order to get to this finishing point over there. You can't touch the walls. Now, some assumptions we're going to make is the robot actually is only a point. And so we don't have to worry about his thickness grazing the wall. It's just he can't pass through a wall. Okay. So we couldn't put him on a path that would hit that point exactly right there or any point on that wall right there. And then as far as the robot's movement goes, so let me copy this into my screen. Page, copy. Let's grab this particular version. And every time you load the problem, the walls are a little bit different. So, so your problem's not going to look exactly like mine. The walls will be slightly different lengths and slightly different positions. The robot starts off facing to the right. So that's his initial direction. Okay. So if I just tell the robot to move 2 units, he's going to go from here to there. Okay. So if, let's say I wanted to get him to this point right up there, I would have to tell the robot 2 things. I would have to say rotate in that direction and then move out to that point right there. So I'd have to tell the robot what r and theta is to get to that point. So now the robot is currently facing in that direction. I'm trying to get him over to this green point in as few moves as possible. So I want to get him somewhere in this region over here. Okay. So let's say I think I can make it to that point right there. So now I have to tell the robot, say, okay, I want to get you from here to there, and it looks like I'm just going to miss that right there. And so now I have to say, okay, rotate in this direction. So this is my theta 2, let's call it, and this is my r2. So calculating the distance between those points is no big whoop. You guys can do that, no problem. The trickier part is explaining to the robot how to make that turn right there. Okay, so I'm going to pause the recording here, and then what I want you guys to do right now is let's take a look at this particular example and see if we can come up with his first and second angle, and then I'll set you free. Oh, I can't pause the video, can I? We'll just let it play. So those of you online, this next part is going to be kind of boring. So, to do this, I'd have to impose a coordinate system, right? Like I might make my origin right there. So 1, 2, 3. This is 4 units over. 5, 6, 7, 8. This wall over here is 9 units over, 10. That point's at 11, 12, 13, 14. That's 15 units over, 16, 17, 18. I think that's 19. Correct me if I miscount. 20, 21, 22, 23. It looks like 24 is the total width of the grid. Coming up, let's go just 2, 4, 6, 8. So it looks like it's 9 units tall, if I counted right. Yeah, I think I calculated that right, or counted right. Calculator needed. Anybody get a rough angle there? I'm getting 0.64-ish radians. The catch here is we're supposed to give the robot degree units, so I'm going to have to multiply that by 180 over pi. So I'm getting about 36.87 degrees, roughly. Now, there's a few ways to come up with that second angle. Anybody have thoughts on the second angle? Kezia, what do you got?
So you calculate the next point, and then you get the angle, and then from that angle to that angle, so I got negative angle, and then you have to pretty much add them to get, and then you minus an angle.
So you're considering like drawing a horizontal component there, and this angle right here is our first theta 1, right? And so we just have to calculate kind of rectangular wise. I have to drop down 1, 2, 3, 4, 5 to get here, and then I have to run 1, 2, 3, 4, 5, 6, 7. So if I consider from that point right there, I have this new triangle that looks like this, where I'm running 7 units, and I'm, let's see, dropping 5. Is that what I counted? Minus 5. So we would there want the arctan negative 5/7, which will give us this angle right here. Right, I'm going to call that alpha for now. Alpha is going to be a negative. So if I take alpha minus theta 1, that says turn that full rotation there. Does that sound right? How do you want about it? Does that make sense? Yeah. So we can calculate that next angle. So the goal of the exercise is in as few moves as possible, and I think the fewest move possible is 4 moves. We would pick some points up here maybe, or there, so that we don't hit the walls. I think I could probably make that point right there. Try to connect them with a line. Line, please. Does that work? Yep, that'll work. And then I have to get from there over to that point right there. So then we have to calculate. So again, the trick here is just consider that the robot is currently facing that direction. What angle does the robot sweep? So we kind of has to go, there's a lot of special equivalent angles. Like these angles right here would be called what, alternate, let's see what they'd be. Oh no, those would be corresponding angles because they're in the same position relative to the parallel lines made by y equals certain numbers. And then the robot's facing this way, and we need to tell the robot to sweep back. So that's our old angle there. So each time you have to calculate a new piece of the angle and combine it with one of your previous angles. So in the homework, for you guys, for each move, you'll say, okay, given that he's initially facing to the right, how far should he turn? How far should he move? Based on that new direction, how far should he turn again? How far should he move? And so you get to do that for each 4 moves and see if you hit the mark. Okay. So kind of fun. I think I'm going to stop here and let you guys play and figure it out. Again, yours won't be exactly the same as mine. Every time I bring up a new problem, the walls are in slightly different positions. So I found this incredibly fun. I chose to do
This
this.
one accepts different answers.
Accepts different answers.
Because you could choose different points, which would give you.
Oh yeah, yeah. So there's multiple paths, right? Yeah. So what the system does is it basically tries your path, and as long as your path doesn't hit any walls and it hits the mark pretty close, you got it. So there's a little room for margin of error in there. Yeah. Yeah. So there's not just one single solution, correct? Yeah. I was picking whole number points for simplicity. They don't have to be whole number points. You can pick any point you want in the plane, as long as you stay within the blue walls and don't touch them or run through them. Yeah. Cool.